the James Webb Space Telescope made groundbreaking discoveries. Recently, the Webb Space Telescope uncovered brand new information about the events that took place prior to the Big Bang, posing a threat to some established scientific theories. The Big Bang theory suggests that there was a beginning of the universe, a dense, extremely hot point that then expanded and cooled, allowing for the creation of galaxies, stars, and other structures. This theory is supported by evidence like Hubble's law, which shows that distant galaxies are moving away from us, implying that the universe is expanding. The universe is thought to be approximately 13.8 billion years old. The James Webb Space Telescope has contributed to an exciting advancement in comprehending what might have occurred before the Big Bang. The cosmic microwave background, CMB, radiation is a faint radiation that permeates the entire sky. It is a relic of the scorching heat and light from the early universe. The CMB's uniform temperature is approximately 2.7 Kelvin, with minor variations that reflect density fluctuations in the early plasma. The CMB also demonstrates that the universe was inaccessible to light up until approximately 380,000 years after the Big Bang, when atoms formed, allowing light to freely circulate. The proportions of elements from the beginning, like hydrogen, beryllium, and lithium, align with predictions made by Big Bang nucleosynthesis. The way galaxies are arranged beneath the surface shows that matter clumped together. Stars formed over time due to the force of gravity. The oldest galaxies can be found at the farthest reaches of the observable universe, while younger galaxies are located closer to us. Galaxies vary in shape, size, age, and composition depending on their location and age. Theories about what happened before the Big Bang remain one of the most profound and difficult questions in cosmology. The Big Bang theory describes the universe as originating in a hot, dense state that expanded over time, but it does not explain the cause of this event or what might have preceded it. Several theories have been proposed to explain the origin of the universe, such as the cyclic model, the periodic model, and the pre-Big Bang scenario. Each of these theories suggests different events and reasons behind the universe's birth. The pre-Big Bang theory is tied to string theory, a framework that attempts to unify all natural forces and particles. On the other hand, the no-boundary model posits that the universe has no boundaries in space or time. According to this model, the birth of the cosmos can be seen as a quantum fluctuation, using quantum mechanics to explain the potential histories that determine the universe's structure and properties. It is important to understand that these possibilities are not mutually exclusive and may complement each other. The latest breakthroughs and what they mean. One of the primary goals in cosmology is to determine how the universe came into existence. The latest discovery by the James Webb Space Telescope, the detection of the most distant galaxy ever observed, may be beneficial. Scientists are getting closer to answering this question. The universe follows a hierarchical structure made of energy and matter, initially spread out across space in a consistent pattern. Minor changes were superimposed on this background due to cosmic inflation, which occurred prior to and set the stage for the Big Bang. These fluctuations exist on all cosmic scales. As matter and radiation interacted and the universe expanded, fluctuations in density led to peaks and valleys in gravity and cosmic structure. The greatest fluctuations are detected in the CMB, which contains vital information about dense regions that began to develop under gravitational forces. Gravity doesn't act everywhere equally in the universe. Its effects are limited by how quickly light travels. This means that an overdense region will only draw in nearby matter at any given time. The farther away matter is, the longer it takes for gravitational forces to be felt. The scale of these cosmic structures expanded as gravitational attraction caused galaxy clusters, star clusters, and larger groups of galaxies to form. Large regions experienced enough gravitational pull to collapse, leading to the formation of bound structures. Initial formations included molecular clouds, dust, gas, atoms, and dark matter, eventually giving rise to the first stars and star clusters. The densest regions of space can take up to 200 million years to collapse, while areas with higher initial density can collapse much faster, in as little as 50 to 100 million years. Star formation emits radiation and stellar winds, creating complex environments that make it difficult to predict the specifics of these early structures. Galaxy formation and evolution. The first huge galaxies formed through the merging of smaller galaxies. These structures were observed approximately 320 million years after the Big Bang, and the James Webb Telescope is expected to reveal populations of pristine stars from the beginning of galaxy formation on a larger cosmic scale. However, the physics of individual galaxies plays a minimal role in the development of large-scale cosmic structures. The growth of galaxies and galaxy clusters is largely determined by three major factors: the universe's expanding size, the initial matter density on a cosmic scale, and interactions between cosmic structures. These elements dictate the formation and evolution of galaxies. Internal processes within galaxies, sometimes called galactic physics, have little effect on the formation and expansion of galaxy clusters. Gravity is the dominant force shaping the cosmos throughout history. The role of redshift in galaxy observation. Redshift is one of the easiest ways to locate a significant number of galaxies from the same era. Redshift occurs because light emitted by a moving object shifts toward longer wavelengths. This Doppler shift causes light from receding galaxies to shift toward the red end of the electromagnetic spectrum. When a galaxy moves away from us, its emitted light is redshifted, and the spectral lines move to longer wavelengths. By analyzing these shifts in the spectrum, astronomers can determine the rate at which a galaxy is receding and estimate its distance. This is represented by the parameter z, which compares the observed wavelength to the original one. A higher z value means a greater redshift and distance. By determining the redshifts of various galaxies, astronomers can map their distribution across the universe. This data also offers insight into the expansion of the universe and the evolution of galaxies over time. Clusters of galaxies and the forces of gravity. Clusters of galaxies have been observed moving at velocities ranging from several hundred to several thousand km/s relative to each other. This method contributed to the discovery of nearby galaxy clusters, including the Coma cluster and the Virgo cluster. These clusters are heated by phenomena such as the collision of fast-moving gas clouds and intense star formation, both of which release X-rays. Studying galaxies and their clusters is essential to understanding the broader cosmic structure and the universe's history. Galaxy clusters offer valuable insights into cosmic evolution and the interaction between dark matter, normal matter, and gravity. The discovery of distant galaxy clusters and the measurement of redshift has enabled scientists to track the movement of galaxies over vast distances. As the James Webb Space Telescope, JWST, continues its mission, it is not only revealing the earliest galaxies but also uncovering potential anomalies that challenge our current understanding of cosmic evolution. For example, some galaxies discovered by JWST appear to be too massive and well-structured for their age, suggesting that galaxy formation may have occurred faster or differently than previously believed. This has significant implications for our models of the early universe. It prompts scientists to refine their simulations, reconsider the role of dark matter, and re-evaluate the processes that drive rapid star and galaxy formation. These observations might point to unknown physical mechanisms or the need for adjustments in our existing theories of inflation, gravity, or particle physics. Probing the first stars, Population 3. One of JWST's key missions is to detect the elusive Population 3 stars, the very first generation of stars formed after the Big Bang. These stars, their eyes to be composed almost entirely of hydrogen and helium, would have been incredibly massive, short-lived, and influential in shaping the chemical composition of the universe. So far, direct evidence of Population 3 stars has not been found, but JWST is capable of detecting their indirect signatures through their impact on surrounding gas clouds and early galaxies. Discovering these stars would offer crucial insight into the transition from a pristine universe to one enriched by heavier elements, the building blocks of planets and life. Unraveling the role of dark matter and dark energy. In addition to exploring ancient galaxies and early star formation, the James Webb Telescope contributes to understanding the mysterious components that dominate the universe, dark matter and dark energy. While dark matter helps bind galaxies together, dark energy is thought to be responsible for the accelerated expansion of the universe. By mapping the distribution of galaxies and observing the bending of light through gravitational lensing, JWST allows scientists to infer the presence of dark matter in regions where it cannot be seen directly. Similarly, the rate of cosmic expansion measured at various redshifts provides data that helps refine estimates of dark energy's influence over time. Any inconsistencies between these new observations and predictions from current models may point toward new physics beyond the standard model, perhaps revealing particles or forces that have yet to be discovered. Cosmic reionization and the transparency of the universe. Another major area of exploration is the epoch of reionization, the period in the universe's history when the first luminous sources ionized the neutral hydrogen that filled space, making the universe transparent to light. This period marks the end of the cosmic dark ages. JWST is especially suited to study this era by observing the ultraviolet light from early galaxies and quasars, which is redshifted into the infrared spectrum. By identifying when and how the universe became transparent, scientists can better understand how the first galaxies influenced their surroundings and reshaped the intergalactic medium. A new era of observational cosmology. The discoveries made by JWST are ushering in a new era of observational cosmology, where questions once considered purely theoretical can now be tested against data. Every image, spectrum, and data point collected pushes the boundaries of what we know, and often, what we thought we knew. This is not only transforming our view of the early universe but also influencing how we model cosmic timelines, galaxy evolution, black hole growth, and the distribution of matter and energy on the largest scales. These findings feed directly into future missions, simulations, and theoretical developments. As we continue to gather data from JWST and combine it with information from other observatories like the Hubble Space Telescope, ground-based telescopes, and future missions like the Nancy Grace Roman Space Telescope, we move closer to answering some of the most fundamental questions in science. What sparked the beginning of our universe? What existed before the Big Bang? How did matter organize itself into the vast web of galaxies we see today? And ultimately, what is the universe's fate? These questions, once the realm of philosophy, are now within the reach of scientific inquiry. Providing unprecedented views into the cosmos. Providing unprecedented views into the formation of the first galaxies and the overall structure of the universe, this will help us discover not only where the galaxies are, but also all of the processes that led to the emergence of stars and planets. As we keep pushing the boundaries of our knowledge and improve our observational capabilities, the knowledge we acquire will bring us closer to comprehending the source of the universe, whether through the detection of ancient galaxy clusters or research into the cosmic microwave background. Each discovery-related component helps complete the jigsaw puzzle of the universe's structure, evolved from its earliest stages to the vast and complex form we see today. This journey deep into cosmic space and history demonstrates the power of scientific advancement and the relentless search for knowledge. The enigmatic details of what came before the Big Bang and how the universe began are still far from being fully understood. Using instruments like the James Webb Space Telescope, JWST, we are continuously uncovering brand new cosmic pieces of the puzzle. As we continue to make strides in our comprehension of the cosmos, one thing becomes clearer and clearer. The more we learn, the more we realize how much there is yet to discover, from the smallest changes in the early universe to the vast structures of galaxies and clusters. The universe is full of endless wonders, waiting to be explored. With each new discovery, we are one step nearer to answering some of the most fundamental questions about our existence. If you find these cosmic revelations fascinating and want to stay informed about the latest breakthroughs in space research, make sure to subscribe to our channel. Join us as we continue exploring the universe's mysteries, bringing you the most up-to-date information and the most exciting discoveries. Don't forget to like this video and turn on notifications so you never miss the latest space news. Understanding galaxy clusters and their significance. Deepen your understanding of cosmic structures by learning about the importance of galaxy clusters. These massive clusters serve as natural laboratories for studying the fundamental forces that govern the universe. Each cluster provides a unique insight into how gravity and dark matter interact on the grandest scales, shaping the evolution of the cosmos over billions of years. Through the lens of the James Webb Space Telescope, scientists have the chance to investigate further-reaching galaxies and look back in time to the clusters that formed just after the Big Bang. These initial structures are essential to understanding the conditions that led to the formation of the more familiar galaxies we observe today. The James Webb Space Telescope's role. The JWST continues to revolutionize our understanding of the universe, providing unparalleled insight into the earliest moments of cosmic history. Unlike its predecessor, the Hubble Space Telescope, JWST primarily operates in the infrared spectrum, which lets it see through cosmic dust and observe distant galaxies, star-forming regions, and other phenomena that were previously hidden. This ability to detect faint infrared light allows scientists to look back further in time than ever before, reaching into the universe's earliest days. With its ability to capture the oldest light, JWST is offering a closer look at the formation of the first stars and galaxies, shedding light on the mysterious period known as the Cosmic Dawn. Probing the early universe and cosmic evolution. One of JWST's most exciting prospects is its potential to probe the epoch of reionization, an important time in the universe's history that took place roughly 400,000 years after the Big Bang. During this period, the universe transitioned from being opaque to transparent as the first emission from stars and galaxies began. Their radiation ionized the hydrogen gas spread throughout the universe. This transition is vital for understanding how the universe evolved from a dense, hot state to the vast, structured cosmos we see today. JWST's ability to study this time period provides crucial data on the processes that led to the development of modern cosmic structures such as galaxy clusters and the formation of supermassive black holes. unveiling the first galaxies and stars. JWST's ability to detect galaxies that formed just a few 100 million years after the Big Bang provides a one-of-a-kind opportunity to study the creation of the initial stellar populations. These early galaxies are expected to differ greatly from those we see today, containing lower levels of heavy elements and exhibiting irregular shapes due to their rapid star formation. By examining these galaxies, scientists can uncover the physical conditions that allowed for star formation in the early universe, how gas was transformed into stars, and how galaxies evolved over time. The first stars, often referred to as population 3 stars, are theorized to have been composed mostly of hydrogen and helium, the lightest elements formed in the Big Bang. These stars were significantly brighter and larger than those we see today, marking a turning point in cosmic history. When these stars died, they seeded the universe with heavy elements through supernova explosions, providing the raw materials for the next generations of stars, planets, and even life. The importance of dark matter and dark energy. Dark matter and dark energy are two of the most mysterious components of the universe, and their roles in cosmic evolution remain subjects of intense study. While we cannot observe dark matter directly, its presence can be deduced from its gravitational effects on visible matter. JWST's observations of galaxy clusters, gravitational lensing, and the distribution of galaxies at different redshifts will help scientists map the distribution of dark matter and understand its role in shaping large-scale cosmic structures. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Understanding the interplay between dark matter, ordinary matter, and dark energy is necessary to develop a complete picture of how the universe has evolved, and how it will continue to evolve. By studying galaxy clusters and their evolution over time, JWST will help refine our understanding of dark energy's role in the cosmos, offering important insights into the destiny of the universe. Future prospects and expanding our horizons. As the James Webb Space Telescope continues to collect data, it promises to answer fundamental questions about the origins of the universe, the development of galaxies, and the nature of the dark components of the cosmos. Each observation brings us closer to understanding the processes that helped shape the universe we see today, providing fresh perspectives on the cosmic timeline. The lessons learned by JWST will not only expand our understanding of our place in the universe but also inspire future generations of scientists and explorers. The continuous exploration of space, driven by technological advancements and a dedication to discovery, will no doubt reveal even more cosmic mysteries, pushing the boundaries of human knowledge further than ever before. A new era of cosmic discovery. The James Webb Space Telescope doesn't just represent a technological triumph, it marks the beginning of a new era in cosmic discovery. Its unparalleled capabilities are allowing humanity to witness parts of the universe that were previously out of reach, hidden behind veils of dust or too distant for older instruments to detect. With each new image, spectrum, or data point, JWST is not only expanding our scientific understanding but also reshaping our philosophical view of existence. It's showing us that the universe is far more dynamic, complex, and awe-inspiring than we ever imagined. Unraveling the lives of stars and planets. Beyond the early universe, JWST is also helping scientists study the life cycles of stars, how they are born, how they live, and how they die. This includes observing stellar nurseries, the swirling regions of gas and dust where stars ignite, as well as supernova remnants where massive stars have met their explosive ends. Even more remarkably, JWST is contributing to the study of exoplanets, planets orbiting stars beyond our solar system. With its powerful infrared instruments, it can analyze the atmospheres of these worlds, searching for chemical signatures such as water vapor, carbon dioxide, methane, and possibly even indicators of biological activity. Looking for signs of life beyond Earth. One of the telescope's most exciting roles is its potential to identify planets that could host life. By studying habitable zones around distant stars, regions where conditions might allow liquid water to exist, JWST could help identify worlds similar to Earth. This quest doesn't just answer a scientific question, it taps into one of humanity's oldest dreams: are we alone? While definitive proof of extraterrestrial life remains elusive, the tools we now possess have brought us closer than ever before to answering this question. And even if life is not found in the near future, every step taken sharpens our understanding of how life arose on Earth and how rare, or common, it might be in the cosmos. Building on the legacy of exploration. The discoveries made by JWST are built upon the foundations laid by previous missions, including Hubble, Spitzer, and Chandra. Each new mission adds another layer of understanding, and future telescopes, such as the Nancy Grace Roman Space Telescope and the European Extremely Large Telescope, will continue to expand the frontiers. As technology advances, so does our ability to explore deeper and more precisely. The next decades may reveal not just the first moments of the universe's life, but also open a new chapter in our search for intelligent life, advanced civilizations, and perhaps even cosmic messages from afar, inspiring a global generation. Above all, JWST serves as a beacon of what humanity can achieve when curiosity, collaboration, and innovation unite. It stands as a monument to international cooperation, with contributions from NASA, the European Space Agency, and the Canadian Space Agency, all working together for the benefit of all humankind. Its discoveries transcend borders, beliefs, and backgrounds, uniting people under a shared sky and reminding us that we are all part of something far greater. For students, scientists, artists, and dreamers alike, JWST offers not just data, but inspiration.